Okay, all right. So based on the title that John's still around, I sort of figured maybe I'd talk a bit about some of the work that I've done during my thesis, my PhD thesis in Bonn. And so my thesis had essentially two parts. So the first part was on like shape spaces, and that is basically speech help, interpolating everything.
I will use it. Go.
Yes, so shape spaces was the first part, and some nice images here, and you talk a bit about that in a second. And the second part is what I call shape optimization. So it's like PD, constraint optimization, diffuse interface models, elastic shape optimization, these kind of things. But today we'll focus on this first part. I guess it's more appropriate to this community, and so it gives me a bit more time to talk about these things a bit more in depth.
So you give another
if you want to. I have the slides in your appendix. You can also do it today if you have the time. So it's not. Yes, basically this slide deck is sort of a Frankenstein slide deck. So I put together different ones. I hope the notation is somewhat consistent, but there might be some inconsistent notation. So if there's a question about that, just ask me. Okay, so I thought I'm talking about shape space, so maybe I should first talk about what shape space I'm talking about. Right? So this is a big term that has been applied to a lot of things. And so for me, or in this talk today, a shape is going to be a discrete surface. That means we have a triangle mesh. And for me, triangle mesh at first is only something abstract, right? It's a combinatorial object. You have vertices, you have edges, you have triangles. And then you can equip this with a topology by regarding as an abstract simplicial complex, and then you want this complex, you want this manifold to be manifold, this topological space. And then you can talk about actually realizing this mesh in three-dimensional space by sort of piecewise affine immersions, which go from this topological mesh to actually real space. And of course, they're saying this is a piecewise affine immersion is equivalent to specifying the nodal positions of your mesh in three-dimensional space. And so really, okay, maybe I should say really that here, in this talk, I will really focus on discrete perspective on these things. Really, so I've considered these discrete meshes as the geometric object. I don't really consider them as a discretization of something, which is maybe another perspective you can take, but really here is because of the data that we have, it's really the discrete surface is the object that's there. And so then we can talk about the space of these objects. And then of course, at first we have the space of emergence. So it's simply the manifold of all the emergence of such a fixed mesh. So that's another constraint here. We work with one fixed mesh, so there's no chain of connectivity, and these kind of things. It's always in dense correspondence, as people in graphics would call it, and somewhere else as well. And okay, so you have the space of emergence of all possible emergence, but we want to consider some invariances, especially we mod out special Euclidean group, the actual special Euclidean group. So we mod out rigid body motions, right? So we don't care if the shape rotates, translates in space. That's not what we care about. And then, but see, we don't mod out reparameterization, for example, which would be the case if you talk about these Sobolev kind of spaces. And then the question, of course, is what kind of metric do we put on this now manifold? We want to make it through like really a Riemannian shape space to talk about geodesics, etc. And of course, we could now go to some kind of like Sobolev type metrics or whatever. There's different ways. But the way that we normally take is rooted in elasticity. So we consider these discrete surfaces as the mid-surface of some thin elastic object, right? Think of a sheet of paper or a sheet of metal or whatever. And then this gives rise to an elastic model that gives you, in the end, what we want to have is a discrete elastic energy that tells you, okay, I have two different immersions. How much energy do I have to spend to go from one immersion to another, like a physical, plausible sense?
So in fact, you have a continuous model.
Yes, I mean it's
no, because your metrics come from something which is continuous, and that's why that's why it makes sense if you change the number of no.
Yeah. So the thing is, the metric that I will show you right now in a second, it's really discrete energy, and it's not completely clear that it converts to something continuous. But of course, the sort of the idea why this energy looks as it looks comes from the continuous world, comes from continual mathematical physics. So yes, in a sense, there is a continuous. For this part, there is a continuous model that we have, but after that, it's just right. And so, as I said, you have this elastic energy that basically tells you, okay, from one immersion to the other, I have to spend this kind of energy, and this typically has two contributions, which is the membrane contribution, which measures tangential stretching and shearing, and it scales linearly in the thickness of your object. So this delta is the small thickness of your actually three-dimensional object. And then there is the bending part. Well, just bending, as the name says, scales cubically in the thickness. And for the membrane part, this is actually kind of straightforward. You first associate a triangle-wise constant metric to your surface, just a Riemannian metric on your discrete surface, which is the basic formula from this immersion. Then you can look at the so-called strain tensor. The strain tensor encodes how much the metric changes between these two immersions. And normally, if you would start to do these kind of things in like mathematical physics, then you would talk about two immersions, or you would talk about one immersion and one deformation of this immersion. But in our case, this deformation is completely fixed by giving two immersions because they are in dense correspondence, because I know they have the same connectivity, and I say these things are piecewise affine, so I completely know I can just give you two immersions and the deformation is fixed. So then basically the strain tensor measures the change in metric between the change in metric between these two immersions. So it's the inverse of one metric times the metric of the deformed object. And then to get this into a membrane model that measures the cost of deformation, what you do is you apply some energy density that you will see in a second, this strain tensor, and integrate it over your surface. And in this case, it's a discrete surface, so you can just integrate it by summing over all triangles weighted by the area of the triangle. And so now this energy density has this strange form. It looks a bit daunting at first, but actually, it's if you think about it, it's very easy because these terms do some different, very intuitive things. So the determinant of this object, the strain tensor, is basically the ratio of areas between these triangles. This tells you how much the area changes between of a single triangle between those two immersions.
And what is A?
Oh, A is the strain tensor that you put in here.
So that's a GXX tilde.
Yes, it's the difference between these two metrics, and it's a 2x2 matrix essentially. And so the determinant gives you the change of area of the triangle. And then minus lower determinant basically prevents your triangles from collapsing. So if one triangle gets like a really, really small area, then this thing will go to infinity. And at the same time, this will also go to infinity if your triangle becomes too big, but much slower. So like stretching is easier than like recompressing things. And then this trace part basically measures the change of local length. So it's like a local length element on your surface. So it looks at first a bit horrifying, but it's actually kind of easy. And also, you would not compute it this way. You would actually write this down in terms of like edge lengths and then compute in terms of edge lengths in the end. But this is just like the physical motivation of why it looks this way. And it's called the Neo-Hookean elastic model. And then, so if this is still something that you can really see as discretization of something continuous, what becomes a bit more discrete, we talk about the bending energy, because we have to talk about what's the curvature of this discrete surface that we have. And for this, we use the dihedral angle. The dihedral angle is the angle between the normals of two neighboring triangles. You could also say it's the angle between the triangles. That's depends on your definition, but we use always the angle between the normals. And then it has this form, and why does it have this form and not just the standard angle from point one? Because actually a signed angle, which is very important. So it's signed because this edge that you have under here has an orientation, and this allows you to give you a sign to this angle. And this is very important because otherwise you could just flip it completely from this to this, and the angle between normals would be the same, just have a different sign, and you would pay no cost for it if you compare it. So it's really important that this actually is a signed angle, which is why you need this upper sign formula. And then, okay, so then this is used in the energy like really simply, really easily. It's just a weighted quadratic differences between these angles in the undeformed and deformed configuration, and these are some integration weights, which basically, so it's the edge length of so along the edges, and then over the area which is associated with each edge, which is sort of like small local area element. And this gives you sort of suitable integration weights so that in the end, if you sum all of this together, you get the appropriate units, if I want to talk this physically. But again, I want to stress, you also use this for some more like physical-like projects. And then we once calculated if it's actually doing somewhat realistic and not really. So, I mean, the material constants are not actually very accurate here. This is not what we care about. We don't do accurate physics. So it's more like physics inspired to get like a natural look of things and natural behavior of objects. Okay, so now we have this energy, and now we want to put it into the shape space framework located metric. Yes.
Just because my understanding usually is that in graphics you use a very cheap a computationally cheap approximation of what the real physics look like.
Yes.
And so I'm wondering, like, if you come back to the previous slide, like, okay, here I understand it's a square, it's a square difference, so it's super cheap. And like, do you remember what the real physical model would look like? Like, would it be a strange nonlinearity or?
So if you want to do like a real physical model, okay. So first off, let me say that this is also not completely unphysical, because at least if your reference configuration is flat, there is convergence results in terms of gamma convergence that tell you this goes to actually the Wilmer energy. So like a geometric bending energy. It's a bit limited because your mesh has to be Delaunay, for example. So there's like some strict conditions why this is it's not the best model to use. And then if you want to really do this in a more like plausible way, you would need to have higher order finite elements. So this become like really a complicated expression because you need to differentiate the normal and differentiate the unbending and so on. And so you need at least, I mean, there's some some work on discrete Kirchhoff triangles, which work with, I think, quadratic elements, but really if you want to do it higher, it would be like C3 elements to actually do this kind of things. So that's, would be kind of expensive to actually do this, probably.
Also, another question. So you say that it's sine angles.
Yes.
And that's very important. Do you think that your surface has to be oriented?
Yes. Okay. Yeah.
And I don't see any physical interpretation of the fact that it's oriented, because bending energy, it looks like.
Yeah, but bending energy, you don't. Okay, so bending energy, you cannot just use, for example, mean curvature, because for the same reason, you need to talk. But for proper bending energy, you need to talk about shape operators. Meaning you really talk about the second fundamental formula for surface, and that's somewhat reflected in the sign of this diagonal angle. So it's
But if you imagine a surface which is not orientable,
yes,
you still could have some bend energy.
Yeah, but then because then you only need this locally, right? You would only need to have an orientable locally.
Yeah, okay. So you define locally, and then
Yeah.
it's right.
Why?
No, you can define orientation. Even if the face is not globally oriented, you will have discontinuities in the orientation, but you still can orient. That's what you mean.
Yeah. I think that
So you don't need to have an orientation.
Not necessarily, but I mean, okay, so I think that's what happens, but I'm also not too sure because normally all these 2D works, they start with orientable surfaces. That's sort of thing.
Because in your formula, maybe if you change the sign, you have a pi which is. Yes, you need locally to have the. In fact, you could define it with. You have just the diagonal angle is defined for two planes. In fact, you need to have in your orientation notion which just one plane.
Yes, but
here you say because you take a normal, so you need to have an orientation. But you could say is because you can compute the dot product between two planes.
You can, but for the elastic energy, you need to have a sign because otherwise, like this configuration and this configuration would be the same because the angle between these two is the same. So these two would have zero bending energy, which is of course not what you want. But if you talk about signed angles, this would be like positive 45 degrees, this would be negative 45 degrees. So there's really a difference there. Why you need this to really work out. Otherwise, it will do strange things.
Okay.
And that's sort of reflected in the continuous model. You cannot just talk about difference in mean curvature. You really need to talk about difference in shape operator, difference in second fundamental forms to get a proper bending model. It's a bit hidden, but there is some logic into why this is a discrete fraternal. And we talk about this with some more in a second. All right, and so, okay, the space, then now we want to turn this into a metric on our space discrete surfaces, as it's called. A bit misleading the name because it's like one discrete surface and all emergence of it up to the body motions. But so that's the name that somehow is used, not that we use. And so to get this remaining metric from this, what you simply do is you take the Hessian of your elastic energy at the rest configuration. So you take in your elastic energy for both configurations, you put in the one immersion you currently add on your space, and then you take the Hessian at this point. And this will be a positive definite matrix, a semi-definite matrix, where because of course this no deformation is almost a minimizer of an elastic energy, right? So this is really a local minimizer, so it's positive semi-definite, and the kernel is exactly rigid body motions. It will compute it, so it actually gives you a metric on this space modulo rigid body motions. And doing this has also sort of a physical interpretation, which is called Rayleigh's paradigm, which basically saying that if I have an elastic model, models always they don't have a notion of a path, so it doesn't matter how you go from like one configuration to another configuration, it only matters the two configurations. But you can have viscous models that actually have some dissipation along paths and have some notion of a path, really. And then this is basically a model going from an elastic model to a viscous model kind of thing. And it goes back to Lord Rayleigh a long time ago. And then, of course, you can do all these kind of similar things in Riemannian geometry. If you want to talk about geodesics, for example, and you want to compute them, it's often a good way to talk about the path energy and consider minimize of this path energy as lengthenizing geodesics. Then things that we've been doing in Bonn and that my advisor Martin Rumpf and Benedict Würden and others have been working on for a long time is how to actually then discretize time in this kind of things. And we use what's called variational time discretization, which goes back to also like physics models for ODEs. But so essentially what we get out after you play this game as a discrete path energy for discrete path steps is just the consecutive energy between like really these two submergence along the path. And that's very easy to write down and something you can optimize. It's still not completely easy to optimize because now you have like multiple shapes, so your number of degrees of freedom is pretty high, and so this, and even though this is more or less easy, it's not super easy to compute, and especially if you want to take like higher derivatives like Hessians and so on, it's a bit of work, but you can actually optimize this. And I guess with Autodiff you could do it for you as well nowadays. And then of course you can use this. They have extended this framework to also get to like a discrete notions of the Riemannian logarithm, which goes of course from some shape to the tangent space to get a discrete notion of a Riemannian exponential to shoot geodesics in some direction, and sort of why this space is used, or why is this a nice space, because it really gives you for like complex surfaces such as this elephant or also this hand, it gives you like really nice physically plausible animations, right? And there's like no notion about like how this object really works in a physiological sense, but still the animation looks pretty plausible, and also the extrapolation and so on. So it really gives you a sort of a nice framework in these graphics applications to talk about shape interpolation, shape extrapolation. And then if you want to, you can also do things like parallel transport on top of this, charts data, whatever, favorite kind of letter. And yes, so this is basically the space that we've been interested in.
And can I ask you a question, especially about the extrapolation part?
Yes.
Because, you know, I think most people in the room here are familiar with the shape metrics, like whose formula as a metric is very complicated, but for which the formula of the cometric, so the inverse of the metric tensor, is very easy. And so it means that, like, you know, everyone is very used to Hamiltonian formulations that allows you to extrapolate simply. And then, okay, like personally, the only thing I know is that when you have a good expression for the metric, then, okay, to find a geodesic, you can discretize the trajectory, and so it will allow you to find a good interpolation. But then how do you extrapolate, you know, with those kind of algorithms? If you don't have a very simple way of continuing the ODE? Or like, do you compute the Christopher symbols and do everything?
No, okay. So in this framework, you compute nothing about the metric. The metric, you know it, but you never use it, basically. Yes, only will use it if you go to the tangent space to do something in the tangent space. But for these computations, you don't use it because you can already see this metric is second-order derivatives of this elastic energy. And if I want to compute with it, agree with the metric and write down everything in terms of metric, I would need to differentiate it further. And I would need third derivatives of this object, and I don't want to compute them. It's just annoying. So this whole framework is built on not using metric, but only using this elastic energy. And then what you do to get, for example, the exponential map is, okay, you start in this exponential map scenario, you have 2 points that you know. And you know that if you want to extrapolate the exponential map, this new point that you will get, together with the first choose one, this should be form a 3-point geodesic. So it should minimize this path energy for k equals 2. Because you have 3 steps, you have k 2 steps, so it's 3 shapes. Okay, and now you know I want this to be a minimizer of this path energy with respect to the middle shape. You can write down for this the Lagrange equation, so the minimizing conditions, which is basically the geodesic equation in a sense, but now in a discrete sense. And then you can sort of look for roots with respect to this equation of the last shape.
Okay. And in practice, like, do you handle it as an arbitrary objective function with LBFGS, or actually you have a very nice quadratic expression, and so you can use conjugate gradient?
So no, it's a nonlinear optimization problem. So Newton's method is what we use to. I'm sorry, it's a nonlinear problem. It's a nonlinear root finding problem. Then the expansion map. So you use Newton's method to do this, which is we'll talk about this. This is okay. So the downside of this framework is, as you said, for example, in the other frameworks, like sometimes like shooting is like very cheap and it's can do this quickly. You cannot do shooting quickly here. It will take some time because you have to solve all these nonlinear problems to get to the next step, and then you need to do it again and again and again, right? And there is here a strange effect that, for example, if you want to compute a very coarse exponential map, like with very big time steps, this can be more expensive than computing more time steps with a smaller distance, just because Newton's method will converge much faster if your step size is small. Because of course there's like a quadratic speed up and so on if you be closer to the real point. But still, then of course at some point there's a limit that you can tune your things to, and so it would take some time to actually do this. So for example, I don't know, if you really want to research some times in a second, and these examples you have to quickly like evaluating exponential level will be on the order of seconds, like 5 to 10 seconds, let's say. That's sort of a realistic thing for these graphics applications.
Okay. And in practice, when you say Newton method, like, are you super clever with the way you implement the Hessian? Like you factor it because it's sparse and blah, blah, blah? Or do you just build it as a sparse matrix and feed it?
Currently we just build it as a sparse matrix. Okay. And that is in fact a bottleneck of this implementation right now. We could be more clever because we know we should know the sparsity structure of this matrix. So it's just like tooling neighborhoods and so on, but we don't use this right now to split build this matrix. And then we just throw it into like a Kolmar solver and get the inverse and to factorize it. And yeah. Okay, so yeah. So the thing is, this is sort of the typical framework in which you phrase this, right? And it's all phrased in terms of immersions, described as nodal positions of my shape, right? I say giving immersions the same as giving nodal positions for this mesh. So this is this all framed. But then you have to notice the problem that you have this rigid body motion invariance that you have to care about, that you need. In some problems, it doesn't matter that much. But for example, if you want to talk about like something like tangent vectors, like statistical analysis on this kind of space, you have to always be careful because now your tangent vectors are actually equivalence classes under this action of the corresponding Lie algebra, right? So this is not so easy. And then this was basically the start of the first project that I worked on this direction and actually started my master thesis a long time ago, which we later called in the end non-linear torsion invariant coordinates. And it's basically to address this problem, to find an alternative representation of the geometry of our shapes, of our meshes, that is invariant to rigid motions, and that's then more amendable to sort of statistical analysis, for example, which then will be the second part. And for this, we build on something that's called the Discrete fundamental theorem. So maybe in the continuous world, you know the fundamental theorem of surfaces, telling you, okay, instead of like talking about the immersion of a surface, I can talk about the first and second fundamental form of it. And if these two fulfill certain equations, called the Gauss-Codazzi equations, then actually these completely determine the surface. Or the other way around, they always completely determine the surface, but if they fulfill the equation, then they actually validate and give me a surface. So this gives you and up to rigid body motions almost, of course, because they are not encoded in the metric or second fundamental form. And there's an equivalent for this for like discrete surfaces, for meshes, and where the edge lengths take the role of the first fundamental form, and the dihedral angles that we've seen before take the role of the second fundamental form. And then there's a discrete equivalent theorem from Wang and colleagues from 2012 that says, okay, if you give me a set of edge lengths and dihedral angles, then I have to check first if they fulfill the triangular qualities, which is a given because if edge lengths should describe triangles, they have to fulfill the triangular qualities. Okay, that's not so interesting. But there's a certain other set of conditions, which you'll see more, the discrete integrability conditions. And if these two conditions are fulfilled, then there's actually a surface that you can construct from these edge lengths and dihedral angles, an immersion of a mesh. And the proof is actually rather simple because what you do is you say, okay, I start with some arbitrary triangle on my surface, and I know the edge length of this triangle, so I know how this triangle looks up to rigid body motions in space. They can just 3 edge lengths determine the triangle. And then you can start to say, okay, now I know this triangle, I know the angles of the neighboring triangles, so I know which plane these neighboring triangles have to lie, and I know which edge lengths they have, so I can also build this triangle. And then you can start to build the whole surface like iteratively from like one starting triangle. But the problem is now if you have some other arbitrary triangle somewhere else, there's multiple paths to go there, right? And all these paths have to match up and give the same coordinates for this triangle, otherwise it's not admissible. And you can actually go ahead and break this down, saying, okay, if this has to be integrable, right? So if I take two different paths, it has to be the same. So if I have a loop on my surface, it has to go to an identity. And then you can iteratively break this down to just saying, okay, I only have to consider loops around single vertices. For every vertex, I just have to look at the loop around it and see if this integration matches up in the end. This is true for simply connected surfaces. If you have holes in your surface, then you also need to take care of the holes and need to also look at the generation of your homology group around these holes. But let's make life easy and just talk about simply connected surfaces. And then really to look at this, to formalize this in this local area around one vertex, you look at these what's called transition rotations, which basically tells you from one triangle how to go to the orientation of the other triangle. And it's described sort of in basically this rotation around the internal angle at this chosen vertex and also the hedra angle. So it's completely given by your edge lengths, because you can also get internal angles from edge lengths by the law of cosines. And then you get these transition rotations. And the idea is that if you go around this loop for one vertex, then it should end up to be identity in the end. So you multiply all of them up, and then you won't have the identity, because then this loop closes and you really get, so if you go around the loop, you really have identity in the end. So it gets the same triangle again as you started with. And then if you require this for all vertices of your mesh, then we can guarantee that if this set of edge lengths and the hedra angles actually is integrable to give you a version of the surface. And typically, you would not implement this, of course, with rotation matrices, but with quaternions, for example, to get a more efficient way of implementing this. And then these conditions allow you to reformulate our space you're interested in as actually simply an implicit submanifold with an Euclidean space. Because we now, instead of like saying, okay, our space is for all these null positions, we look at now edge lengths and hedra angles, and this is a space of 2 times the number of edges dimensions. And then the manifold I'm actually interested in, which then is isomorphic to the other one, today it may actually be the one I've talked about before. It's the one where we have just all of these, which are fully triangle quantities, and it's discrete mobility conditions. And of course, these triangle qualities, they form an open subset. They form an open convex polyhedron of the space. So for like differential structures, they don't matter. What's really interesting for like differential structures is this tunability conditions.
Can you say again what it is exactly? So it's you say 2 edges? No, it's
2 times. So it's for each edge, it's the edge length and the hedral angle. So the angle between the neighboring triangles. That assumes a bit that your surface is actually closed and doesn't have a boundary. Otherwise, we talk about internal edges only. So I have an immersion of my mesh, and I compute all the edge lengths and hedral angles, and this gives me a sort of alternative representation of my geometry. I can actually show that I can also go back if these conditions are fulfilled.
Yeah.
It's actually these 2 spaces saying all the immersions after rigid body motions. It's the same space as talking about this implicit submanifold here. Well, it's a bit.
this I understand, but I don't understand exactly what is Z. Z is it's the birth edge.
Yes, it's a vector containing all of that.
And Q of Z is what is okay? This is the probability condition, but
Yes.
it looks like what you say.
So it's a vector value thing, right? So it has a number of vertices conditions, and then you can now start to play. So you can now look at this and really compute. So it's okay. So it's actually it's not number of vertices. It's 3 times the number of vertices, because you have quaternions and you want it to be the identity. So you only take the imaginary part of the quaternion, and if this is 0, then this is an identity rotation.
Yeah, but to get the quaternions, you have to, because this is to encode the rotation.
Yes.
And so you have the transformation to go to the quaternion. It's not something which is totally trivial. Given just the length and the angle, you have a transformation, huh?
Yes. So I mean, implementing this is not trivial, let's say. And I mean, so you get all these rotations. So you get these one neighborhoods of your vertices. You get all these rotations around, so like 2 rotations per edge. You have to multiply them up, and you can of course all do this in like in quaternions. But all of them are basically also
No, because it's a formula using quaternions.
Yes.
The quaternions are themselves, a formula. You need a mapping from the things to the quaternions.
Yes.
Okay, and so at the end, it looks like what? It looks like something just polynomial. No,
It's completely non-linear.
it's really
Yeah, it's nasty to implement. It's nasty to differentiate.
No, but this is something you can compute just for what you have no fixed point inside, or it's just you have a formula.
Yes.
Given Z, you can.
Given Z, you can compute this, and it's also not too slow. It's not super horrible. I mean, usually it's faster than, for example, the elastic energy. But yeah, for example, to make this be computable quickly, you have to spend some time to implement it correctly. And you have to send, especially if you want to have derivatives, when you have huge products here, right? And each of them depends on that, right? So you really, you have huge, you have to venture out of this. And maybe nowadays you could do it by autodiff. Maybe this would work well. But when I implemented this, it was not as advanced. I tried, it didn't work that well. So I did it all by hand. So really, you calculate the derivatives for the elementary building blocks using Mathematica to get some formulas for it, which are also horrible because in there you have something like the interior angle, which depends on the edge length of cosines. You have areas in there and so on. So it's a mess. And then you really have to.
Yeah, but the trick is that the energy will be very easy to compute with these coordinates.
Yes.
And that's why you have to take this constraint. This is more or less what Barbara.
Right, so yeah, and then, so the manifold that I now carries is an implicit submanifold of some Euclidean space. And there's a few nice things about it. For example, you can explicitly write down the tangent space very implicitly as just the kernel of your differential, these integrability conditions, right? Which you can compute, as you can actually compute a basis for a tangent space and this shape space, which is very nice because you can really work with tangent vectors and can really do analysis on this tangent space. For example, you can do look at things like infinitesimal rigidity. So it's asking, okay, I have a shape. Is there a way to deform it isometrically? You cannot prove that you can, but you can show if there's no infinitesimal mode that allows this, then you cannot do it. And you also can discover candidates for infinitesimal rigid transformations by looking for tangent vectors which only change the hedral angles and don't change the alpha angles. And for example, you can see for this what's called Steffens polyhedron, which is the smallest polyhedron known to be able to really move isometrically. You can show that this actually can move this tip. You can find really this mode of moving this tip in the tangent space as an isometric deformation mode. And you can also build this at home and play around with it, kind of nice. And then what we also did on this, we used it as a way to formalize, to formulate some optimization problems on immersions by using these primary coordinates, and you get this sort of this constraint optimization problem. And to actually implement this and solve this, there's sort of two things you have to consider. So first, of the triangle inequalities, and here the trick is basically ignore them, because there's two ways you can take care of them. So in line search, if you do some line search based approach, you can just stop your line search short of violating them, because there's an open subset, so it doesn't really matter the differential structure of the problem. So you just have to stay inside and you're golden. And then if you use this membrane energy I've shown you before, there's actually a natural barrier term in there that prevents triangles from collapsing, that prevents you from going away over this triangle inequality. So for us, the solution has been to just ignore it, basically. And then what you're stuck with is a quality constraint optimization problem. And for this, we've been using an Manipur-Gauche method, maybe you know it. So it's sort of a fancy penalty method. And then to really solve these subproblems, use line search Newton type method. So it's basically everything you can, it's just things you can find in your favorite optimization book. So it's nothing too fancy. And then maybe one example that we kind of like to do thing again with this is really isometric deformations. I really say, okay, now I have some reference configuration, for example, in the splash configuration, and I want to really find isometric deformations. Isometric mean a really strict isometric sense that no edge length changes. And now in this, if you really use edge lengths and hedral angles as for your primary coordinates, that's very easy because that's just coordinate constraints, right? You have fixed constraints, your edge lengths, they stay fixed, they don't change. And then you can, for example, here we have some fixed flat reference configuration. You have edge constraints, and you enforce some bending here and here to go to 90 degrees. I think it's 90 degrees. And then just relax the whole configuration and see what comes out of it. and you get this really nice deformation, which exhibits some of the characteristics you would assume from C2 isometric deformations. So the Harbeck-Nierman theorem, which basically tells you that there's either rule surfaces, so it's a developed surface, so it's a rule surface, or there's like flat triangle areas. And that's something you can see, I think, we have rule parts here and flat triangle parts here, and here as well. And so it really gives you some kind of thing. And you can also try to do this with your paper at home, to fold it to like 90 degrees, and it's actually, you can also discover the state of stable state of your deformation for actual paper. Kind of nice. Even though this is not an accurate physical model, it sort of still resembles this behavior kinds.
Okay, and so just to be clear, so basically to simulate this,
Yes.
you use what you presented in the previous slide. So you
Yes.
say, I have my configuration represented in my strange space, which has this, and then minimize the bending energy
Yes.
under the constraints that mean that my strange coordinate actually represent a reconstructible surface,
Yes.
right? And what does a checkerboard pattern mean?
So the checkerboard pattern is curvature. It's triangle integrated Gauss curvature. No, not Gauss curvature, mean curvature. Yes, not Gauss curvature, of course.
Okay,
That's
so I understand where it would be smooth, and then basically it's a smooth signal, and you put a checkerboard pattern on it just so that we can visualize it better.
No, it's really
Oh, it's really
it's not really a checkerboard pattern, but it's just that these vertices going in this direction, you have sort of a curvature, like a mean curvature, and then you see this really the way it's rendered is just like it looks at a checkerboard pattern, but it's not really. Now, if you look here, it's a bit more chaotic because there's a crease within a crease. So what happens here is basically you don't have like a smooth ridge along your whole paper, but it starts to bend inwards a bit, and then in this bend inwards there's another bend inwards, and so there seems to be some microstructure forming. I would actually try to and could never completely simulate this to a sufficient resolution to really see what's going on, because in some experiments you see like another crease forming, so like a periodic structure occurring. But yeah.
So you mean that in the checkerboard regions, basically one triangle in two is flat and one triangle in two is bended?
Yeah, so
Like
basically the whole surface is bent along these like rules. So you can like actually put like lines here, and then the bending is all sort of only along these lines.
Why you say theta I equal constants?
This is basically I said to get some deformation. I say these ones here and here they have some constant value. In this case, 90 degrees. So you to get because now this is the answer of this representation. There's no such thing as external forces in this representation, right? External forces require some configuration with a fixed rigid body motion. So this is not represented in space. This is really an intrinsic model, but really a model without rigid body motion, without embedding in space. So we kind of just simply like, okay, I have forces acting on my object. You need something to form these coordinates. So that's what we came up with to say, okay, we clamp actually things to like a 90-degree angle.
And just to understand also, so in the first part, we presented the bending energy, and so it corresponds to some Neurocan presentation without this new representation. Sorry. So in this experiment, you use your z coordinates representation, whereas before the same code was, the same algorithm was implemented without. So how can you compare?
Okay, so the thing is, you could also do this like nodal positions, right? Say I put isometric constraints on my problem and do everything in nodal positions. The thing is, sort of isometric constraints in nodal positions, they are very numerically hard to deal with. So that's very cumbersome. You could do the same things, but here's like just like easy coordinate constraints. And maybe for example, you remember also the bending energy. The bending energy is just kinetic energy right now, right? So it's just a kinetic difference between these other coordinates here. And also the membrane energy would be simple. We don't use it here because it's fixed, but also we simply expressed in terms of the edge lines because you can calculate all these things like areas and so on. It's a bit of work, but you can do it. So yeah, so it's basically you could also do it in nodal positions. Here it's just much easier and there's much more care about like numerical considerations.
But here, in fact, you have it's not a local problem because you start from something which is flat, Z, and okay, Z. I don't know what is Z. The initial configurations, but okay.
Z star is the initial.
star.
Yes.
Yeah. Okay. So here you are using something. Okay, you are doing this discretization or not?
What do you mean by discretization?
Yeah, you discretize. You introduce some kind of discretization to go from Z star to Z.
Okay, now so Z star and Z are both configurations for the same triangle mesh, right? As I said, everything's discrete.
Yeah, I understand. But the energy, okay, this W.
This W is then just, okay, in this case, it's just the bending energy, right? Because I fixed the edge length, so the membrane part is always 0.
Yeah, so you use it now in a situation which is absolutely not infinitesimal. It's a big information.
Yes.
Okay.
I mean, it's really a non-elastic model in a sense. So it really, it's likely that it approximates like a really truly nonlinear model, elastic model for all surfaces, just not proven, let's say. Yes, but so, okay.
That's interesting.
This is something nice and interesting, but actually why we did this was sort of a different motivation. So the goal I set out on for my master thesis was to do something different. It was to do sort of stochastic statistical analysis on this shape space and do it in an efficient way, in an efficient manner. And this is then something that we built afterwards on top of these coordinates. And sort of now he runs it under the title of Sparse Principle Geodesic Analysis. I'll tell you a bit more about this. So now the idea is, so the goal of this project was to create a data-driven, efficient non-information synthesis system. Basically, what it means is I have a bunch of input data. For my one fixed surface, I have a bunch of input immersions, let's say, right, that represent different configurations. Typical examples here for a humanoid character, you have different motions that a character can perform, like different configurations that can have. They can, for example, from a scan system or whatever. And that's really not our problem. We have this data set and then we start from this data set. And then what you want to, in the end, you want to have some model that allows you to create new deformations of this character or this model that are realistic, right? So they adhere to some more than just elasticity. For example, I mean, humans can only bend at joints, normally at least. And then this is something that's not encoded into the elastic model, right? You've seen that these deformations look nice if I have two endpoints, but I would start to like randomly apply forces to one of these models in an elastic sense. It would not do deform like a human would deform, right? So you need some more information in this model to actually get sort of a reasonable model for human deformations, let's say. And so we want to do this data-driven, so we want to start from this input data, and then at the end have this model, and really want this model, so the goal that we set out with, that this model should be somewhat real-time capable, right? So that, for example, like a typical application is that people have a modeling system, so they have a human model, and they want to change the position, and what they can do is they can just grab something on the hand and move it to somewhere else, and if they, in this movement, you should be able to do this somewhat real-time capable, so let's say 20 frames per second. That was sort of the goal that we set out in terms of efficiency. Because then this is something that people in computer graphics actually care about. If it's below that, well, it's too slow down. And so we will see in a second how we do this, and it's based on sort of some PGA, so statistical analysis on a shape space, and then some efficient tricks to get all these synthesis really fast. So the sort of the core component of this is principal geodesic analysis, and many people will notice, but just recap it. So it's a technique to start with some given the input data points to extract a submanifold of your shape space or a manifold in general that approximates these data points. So it's a nonlinear generalization of PCA to manifolds. And how it works is, okay, you start with some input shapes that you're given or input points on your manifold. Then you first compute the Frechet mean of it. So it's a nonlinear mean of it. In our case, it's simplified to be an elastic mean in terms of this elastic energy. Then you pass to the tangent space at this point. So you linearize your problem by taking the logarithm of your input shapes, which is also in the discrete operation here. And now really, if you talk about these edge length and heat length representation, you can really do this really with tangent space, right? You can really work with tangent vectors, which is really easy to do compared to what we've done before in node positions. And then to get a submanifold, you compute first a basis, like a subspace basis in the tangent space by doing PCA there with respect to your Riemannian product to get sort of the first dominant modes of radiation. So that's why some people also call this tangent PCA. depending who you ask. And then, of course, maybe to recall, so the problem for PCA can be also phrased variationally as this approximation problem, saying for my given logarithms V, I want to find a orthonormal basis U in some way so that this best approximates to given input algorithms. Right, so this gives you an algorithm to create a submanifold by then applying, in the end, the exponential map to your created principles of variation. So this is the basis of my tangent space, but I actually want to have a submanifold. So I apply the exponential map to these tangent modes to get a new submanifold virtual shape space. And this really gives you a way to start, okay, I start with some data points on my manifold. I do this processing, and in the end, I have a submanifold that's parameterized over a tangent space or a subspace of tangent space that sort of approximate these data points. And the idea here in this scenario is, okay, this is actually something we would like, because then this would hopefully well approximate like admissible deformation of a human, let's say. But the problem is, as I talked about before, in our scenario, evaluating this exponential map is expensive, right? So if I want to create a new shape, say, okay, I want to modify something, I want to have a new shape, it will take me an order of seconds to compute it. And this is sort of not feasible for example, in the interactive editing system, right? So this whole goal of this project is, okay, actually, how can we keep this and get a very fast and efficient parameterization of the space in the end, which we can evaluate in terms of milliseconds. And so the first thing that we did is we introduced some more structure into these modes by going to something we call sparse geodesic analysis. So you basically do the same thing as before, but instead of doing this PCA problem in the tangent space, you create a sparse PCA. So you had a L1 sparse realization, so they can sparse modes. You have to do some other things now, technical things like force your modes to be in the tangent space because they're not guaranteed for that anymore. And you have to control the weights that you get so that they don't always get super small and the weights super big and so on. But basically it's about, okay, you want to have sparse modes because you promise for us, okay, maybe if we have some more structure and then we can do some more clever tricks to cross things. And then actually maybe some examples here, some modes that we actually get out of this kind of approach for the data sets in the beginning, so these humans, and you can really see how it's also, they have some nice semantic meaning if you do this in, okay, maybe let's take a step back. So this L1 term really is also in this edge length and the hedral angle representation, which is really important because there sparse makes sense because it has a physical distortion interpretation. It's changing of first and second fundamental form, whereas in nodal positions it would not have such a nice interpretation. Which you can, for example, see, for example, this deformation here. This is definitely not sparse in nodal positions, right? So the whole leg is moving, but in edge length hedral it's pretty sparse because only you mostly change the angles at this point to like move the whole leg. And so you see that this gives you like nice semantic plausible deformations in different arms and legs, here the other leg thing, and so on. So really sort of oftentimes you see that these correspond to some joint or something on the body, which is just coming from the data. So there's no guarantee for it to do this, but that's something you typically observe, which is an added nice bonus if we would like to have.
And otherwise, if you don't do this,
yes,
you do not impose sparsity, would you observe sparsity in the data?
No. So if you would not have a sparsity constraint in all of these, the whole body would move somewhat differently. They would always move in some different directions, everything at once.
Yeah, but you since you like you say, I mean, we have articulations, you know. So,
yeah. Okay. So okay, in that sense, it's somewhat sparse. Yes. So it will be focused on like joints where it actually happens. Okay. So it's sparser than really everywhere, but this still have like significant large regions and will all these regions at once. So it's not really sparse. And so the idea is now, okay, we have now this sparsity. Can we somehow exploit the sparsity to build a more efficient approximation or an efficient approximation of the exponential map to get really speed up in the end? Because the idea was, okay, maybe you can sort of look at only that you only have to care about things that are close in support, and if things are not close in support, maybe it's just easy to approximate. And in fact, it turns out that is the case. Because let's now look at this a bit more in this like simple example. It's just these three different modes. So yeah, mode A is in the right arm, mode B is moving in the left leg, and mode C is in both arms. But so there's a strong overlap between A and C, but no overlap between A and B. And we observed that if you have two modes that do not have strong overlap, you can actually approximate the exponential map in terms of edge lengths and hedral angles of the sum of these two modes very well by just summing the result of the exponential maps. So really, this thing holds approximately up to, okay, so it's affine sums because you have to look at the difference to some reference configurations with mean, but really you can, by affine combining these exponential individually for these two shapes, you can get a very well approximation of the combined exponential map. Yes?
I didn't have sense of how these modes are selected. How the modes are selected. How do you select them?
Okay, so in this previous, so we just, okay, so it's basically just this solving this problem in the tangent space, which means you compute the first dominant modes of variation, like in the PCA on the tangent space. But now the additional constraint is you have to sparse these things, so really you have to solve for like a basis of, let's say, J modes at once that are sparse and approximate your data well, where data now is logarithms of data. And then you get this.
But when you say if there is no overlap on the next slide, which
Yes.
is that you may have the modes that overlap, I mean the motions that overlap?
Yeah, okay.
Are they orthogonal?
Yeah, so okay. So for this example, I selected manually, and you can also do this automatically because you can sort of measure sort of the area where there's support of deformation, and then really compute if this overlaps just by sort of like the point-wise product of things. And then you get a notion of sort of how strongly they overlap, and that seems to be a good indicator if they are close. And then you have to group them somehow and find them somehow.
I understand you. All this is to speed up the calculations, but at the end of the day, you need to combine all of them, right?
Yes.
To get combined motions.
Yes.
All this.
That's a very good point. So what I've shown you here is basically, what I'm saying here is you can repeat this. So no, here is an area estimation for this example I've shown you. You can really see that for the combination of A and B, this summing gives you a perfect approximation. Where always in this example I show you an approximation, I will show you a purple point cloud for the true object that it should be, and sort of a yellow shaded surface for the approximation. And really you can see, you don't see any difference, right? So all these purple points are perfectly on my surface. And if you take some modes where this doesn't work well, then really you see a difference, for example, here in the arm where there should be, they do not agree, so this is not a good approximation. So this really depends on like having a spatially separated support. And then you can, sort of the idea is to repeat this, right? So like to take all your modes, now split them into different subsets of modes that have, so that these different subsets do have different disjoint support. So you have like here in this case L groups, and these groups should pairwise have disjoint support. And then you need to combine them, which you do by summing the exponential map for each of them together. And this gives you sort of good approximation of the exponential map. There's a small caveat that, so if you just sum them, there's of course no guarantee that you are actually on your implicit submanifold that we're working on. So you work in the implicit submanifold and change the Hebrew angle, so there's no guarantee that you're on there. So you have to project back somehow to really get a point on your implicit submanifold or to reconstruct these nodal positions. We'll talk about this a bit more when we actually get to like practical implementations. And now you're right. So now I have to actually make my problem worse by now. Because now to evaluate this, I don't have to evaluate one exponential map, I have to evaluate L exponential maps, right? And each of them is more important, it costs the same as the exponential at the beginning. So I make my problem by a factor of L worse. But the thing is, the hope is, and I'm going to show you this now, that actually I divided my problem up. Then now I have a lot smaller problems where I can actually approximate the exponential map cheaply in different fashions. And then I can have a cheap approximation for all of them and combine them cheaply in the end to get a cheap approximation overall.
Just remind me what NRIC is the acronym of.
So this is edge lengths and dihedral angles. So this is nonlinear rotation invariant coordinates. So that's our abbreviation, because always saying length and angles is a bit cumbersome, so we switch to NRIC most times. For some audience, it's easier to work with length angles. Yeah, but this is this NRIC, this length angle space we've seen before with this implicit submanifold of this high dimensional space.
And just because, in my mind, it was always, okay, that's the space of manifold triangle meshes.
Mm-hmm.
And then, if you have a deformation, the second deformation, if you add them together, how would you not end up on a real triangle mesh?
Okay, so
I'm reading.
So you can, of course, if you think about deformations and like nodal.
Yes, but it's more like if you add the dihedral angles together, then you may run into.
Yes, exactly. So adding In like node positions, you can always add, and you will stay on your space because your space is just the whole dense object. Okay, but it will look horrible because like these linear interpolations of shapes they don't work well, especially if these like strongly articulated shapes. But the observation is that actually in these length non-hydro angles, sort of adding things in a like local neighborhood is not too bad. You can locally operate linearly in the space oftentimes, because it's rather flat, your manifold. But you do have to project back because then you will get something that's not admissible because you have a curved implicit submanifold that you're working on.
Yeah, can you say to us something about the fact, because we have always that constraint, because QZ equals G.
Yes.
And so on. And so here the fact is we're adding in that. Okay, can you
the constraint
a little bit about that?
The constraint will be violated. So this will not fulfill the constraint. And maybe if you're lucky, then it will, but it won't. And like there can also be a case that it violates trend inequalities. Maybe that can also happen. But then basically this is why we project back, and this projection just means find the closest point that fulfills these conditions. And this is basically this projection operator, which at first also sounds cumbersome, but as I said, for example,
you're projecting on the manifold.
Yes.
The projection.
Yes.
So it's
this can be. So if you want to do like that, it's not maybe the smart operation, but we'll see in the end. We need to go back to like vertex positions. We do need to get back because to render these things, we need to have vertex positions. To interact with them, we need vertex positions, right? And so going back to vertex positions, actually it's the same problem in a sense as projecting onto the manifold. Because if I compute vertex positions that match of this thing, this is the same as finding the mismatch configuration. So we delay that problem to the end when we actually need to go back to vertex positions, and then you can see how to do this.
And for the exponential, in fact, you have this trick that you are using when you are using the discrete Riemannian geometry, where you say you have 3 points and so on. But here you have this problem which is nonlinear in sense.
Yes.
And you have to solve it, in fact, with the constraint that you need equal to 0. So you have to look for that.
You have some also this in this geodesic problem here. We have some these constraints also in this shooting problem.
No, but that's the price to pay to work in some kind of implicit parameterization which this is a good idea, but in fact you have to pay.
Yes. Okay, so as I said, now we've divided our problem and made it worse, but now let's make it better. And so we've sort of in the passing of time, we've come up with 2 methods to make it better. First let me show you the results. Actually, this grouping that you get out of this, for example, these modes you've seen before, and actually sort of semi-automatic view, okay, those are 2 in the same lag. This is also in the same area of the body, you have different arms, and this is also more like a 4-arm thing. So we can group them and gives you some nice configurations. And then really to make the steps to this everything be efficient, we come up with 2 ways, because now we have to approximate these exponential maps on each of these smaller subspaces. And the first thing that we did, the first approach is actually just do this with a grid. Just compute a lattice of points in this like small space, which is feasible if it's maybe like 2, 3, 4 dimensional. And then if I want to have pre-compute the exponential map on all of these lattice points, and then if I want to have a new point, just do like a multilinear interpolation of the grid cell that you're in, based on your weights where you actually are. And this works well up until dimension 4. Supports very fast, but you have to pre-compute this lattice. So this is something you have to do beforehand. Just takes some time, but it's also something you can easily parallelize on a big machine, right? So if you have just for like 1,000 lattice points, just take a machine with or like multiple machines with 1,000 cores at once and just do it in parallel. Your weights a bit, and that's okay.
Okay, and just to be clear, these interpolations, you never mean in vertex space, it's always in implicit coordinates.
Yes.
And then, so like taking the average is easy, and then you pay the price of projecting back to
Yes.
Yeah.
So last few.
No, sure.
Because of this grid, so here you show 2D, but in fact, it's how many dimensions?
So it's for us, it was feasible up to 4 dimensions. Because also, of course, you don't grid your whole space, or if there's a limit on how far you go along these modes before deformation become a natural, there's a limit on how far I can move my arm. So there's like a compact domain actually in the end. And 4 dimensions is feasible, but after that,
Yeah.
So when we computed the splitting of subspaces, also in these examples in the beginning, said, okay, we only take splittings when the maximum dimension is 4. Everything else does not work. And there's another disadvantage because you have to store this lattice. You have to store these grid elements, right? And this can become quite big if you have like a lot of them and you can have a fine mesh. But actually, the approximation quality, if it works fundamentally, then the approximation quality is pretty good. But to tackle this problem of the high dimensionality, we actually did something else. We did everyone's favorite trick. We went to neural networks and used them to approximate this kind of thing. And maybe we talk about this a bit more, because I think the grid thing is not that interesting. For this network kind of thing, so we go back to the problem. Okay, so the idea is we want to approximate the exponential map on this SPGA space by some function that is cheap to evaluate, right? And before, as I said, can do grids and affine combinations, but now we want to do this a bit more for like larger dimensions beyond 4, and also maybe a bit more overlap. That's maybe a bit more tricky in the previous setting. You can formalize this as a sort of very stupid variational function approximation problem. You can just write it like this. So you want to find some function that integrated with the domain has like small error. And you can formulate, okay, can say, okay, now I can't evaluate this integrate exactly, of course, on my problem exponential map, but I want to approximate by some sampling, which is somewhat akin of this grid elements that I did before. And sort of so far we said, okay, doing splitting into subspaces and doing for each subspace a grid interpolation and then just combining them by adding together, that gives me sort of a good candidate for this function. And now the second part, the idea is, okay, maybe I can use neural networks as a candidate space for these functions and use them to approximate the exponential map efficiently. And right, so but the idea is we try this, you can try this naively with one network, and we'll see in a second it doesn't work that well. So it's surprisingly bad. And so then we had the idea, okay, maybe we can carry over what we've learned so far, and we can also apply this divide and conquer strategy and carry over the splitting into different problems and different subproblems that are easier to solve. And then try to approximate the exponential map by a network on each of these subspaces, and then have like one other network that actually combines all these estimations to get one final estimation. So you can write this down. It's really, again, these problems are extremely simple to write down. It's nothing fancy in terms of neural networks. It's really basic stuff. So we start off with, okay, you want to approximate the exponential map on each of these subspaces. So you take some samples on these subspaces, and typically these are related to all the other samples we had before, and you just approximate the exponential map there with a linearly sparse problem. You do this, you optimize a network with your favorite algorithm, your kind of basic, like fully connected network. You do this, you get very good approximation quality with a small amount of samples. And then you have another network that takes as input all these outputs from these like small approximation networks for all these problems, and you combine them together to approximate the output of the exponential map, which is ZI, which is from the previous slide actually, not this notation. So the ZI is basically the output of the exponential map you would like to have, and then you have an approximation by only subspaces, and then an element that combines them together. Maybe you can also show this as a nice visual representation. You start with a bunch of subspaces. For each of them, you find the blue part, fully connected neural networks to get sort of approximations of the exponential map on them. Again, everything works in these edge lengths and dihedral angles. And then you have another network, this is this yellow one, that takes all these approximations, which are now, let's say, 10 or so, and combines them together to get one final approximation exponential map. And here, you can be a bit more clever and do things like using graph convolutional neural networks to actually do this combination, because now this is data on your mesh, and so you can be a bit more clever here and to be a bit more space efficient than memory efficient and computation efficient. And this works very well. So maybe here's an example of a complex shape. So because I said before, maybe remember this model I used in the beginning is this human didn't have hands. And there's a very well reason for that. We could not approximate hands because hands are too complex added to the rest of the body to do this with like 4-dimensional spaces. So this wouldn't work. And so this is really like another model now, which is called SMPLX, where we have like 150 input shapes from some data set from the MPI in Tübingen, which actually create these by scanning and so on and cleaning the meshes, etc. It's a huge process. And then we create actually extract from that 80 modes using our Sparse PGA approach. And then we split them into 10 subspaces, where the biggest subspace has a dimension of 24 now. So that's considerably bigger than 4. And actually, even the smallest one has dimension 3. So it's something that would not be feasible with the grid, but it's feasible with the networks. And then you can see it really, especially for these high detailed structures. For example, if you just take like one fully connected network that tries to approximate the exponential map on this 8-dimensional space, it does not very well, right? So I mean, you can see the problems in the end, of course. So the overall body is fitted okay, right? So it's not too bad. But you can see a problem in the hands, typically also here, or also maybe in the feet. So the high detailed structures, it will suffer really from approximation problems. And the same thing is true. So this FN combination is basically an approximation what we've done before. We're taking exact evaluations of the exponential map because we can approximate them by grid. So we basically give like an upper bound quality by taking exact evaluations of the exponential on each subspace and then adding these results together. And you see, maybe it actually does better than this fully connected network for everything at once, but there's good problems. But then if we do our divide and conquer strategy and approximate the exponential map on each space by a neural network and have a combination network in the end that learns this combination, then you can see you get really nice approximation results. And also you can see this in sort of like the quantitative error measures that you can do. And maybe why we're doing all of this, so to come to the fun part, yeah, let's skip the overview. So maybe see some results of this at the end. So really what you want to do in this kind of things is sort of, for example, an easy application is interpolation. You have just some curve on your, your subspace, and you want to have a quick, you want to quickly get really this thing as a deformation. All right. And so now we come back to this problem of projecting on Submanifold, right? Because now I can do all this interpolation, I get like nice edge and heater angles, but I want to look at them. So I need to reconstruct basically these nodal positions. And you do this just in a very stupid nonlinear least fashions, in a sense, right? So for a given point here, that a given pair of edge and heater angles, which in our case output our approximation algorithms, which is capital Z, you look for nodal positions such that the corresponding edge lengths and the heat lengths to these nodal positions best match your target ones. And this is, you can solve Gauss-Newton methods and nonlinear least problems. So there's some weighting on the metric to be a bit more precise, but that's not important. We can solve this by Gauss-Newton. It's a very easy thing to do. And the thing is, if you have like a good instantiation for your method, for example, in these deformation things, you have the previous time step, then you can get away with like one iteration of this, which is like 20 milliseconds. And this basically takes like no milliseconds of time, like 2 or 3. So overall, we can do this for each time step with less than 30 milliseconds. And then this allows us that these deformations now are actually computed sort of in real time. So the frame rate of these videos matches the computation time you need to actually compute these shapes, starting from this path that you have in slow dimensional space. But maybe,
what is the command? The command is what? Okay.
You mean so the
Now yes, what we see, you have the inputs, you have some kind of scenario for the input parameter.
Yeah, so the input scenario is you have in this case you have some example shapes on your smaller space, and then you just compute a spline between them on your low dimensional subspace of your tangent space. And now you want to have this in the computer, of course, computing the spline. It's also very fast. Also in no time, it's just basic. I don't know what kind of spline I used here. Just some spline and like R to the in this case 20 or something, 20 modes. So it's a spline, and then we reconstruct actually the deformation that corresponds to it.
And how many nodes you have in your defined spline? Yeah.
I think the number of time steps is something around 100. Yeah, but
no, just the interpolation. So you interpolate. Okay, but how many? To define the full movie. So how many?
Okay, so the input time steps would be like 5 or 6, I think. I think something on this on the order of 5.
And so you're looping.
Yes, this is loop. But maybe a bit more interesting problem is actually the editing problem. Yes.
Out of curiosity, like, what software do you use to render the hands? 2D?
No, this one's actually rendered ParaView.
Okay.
But newer figures, that's one before I actually done with Blender. So I moved up in the world from PowerView to Blender. Very nice figures.
Because they are adding all of this super fancy physics-based rendering now in PowerView. So the hope is that you won't have to learn Blender.
Yeah, but my problems with PowerView, why I switched actually because they changed something, and so they removed some of the NVIDIA ray tracers or changed them, and now I can reproduce this kind of examples. I can reproduce the look of this with NeoBlender, and I'm doing PowerView regions. And then I decided, okay, that now is the case, I can also switch to Blender, because also Blender is not too hard to learn if you want to like create nice rendering. And so maybe the more interesting problem is actually the editing problem I was talking about at the beginning, right? So for example, here you slap a bunch of markers or a bunch of handles onto this humanoid model, like these hands at the head, at the feet. And now you can basically, these blue bubbles, they correspond to like one vertex on the mesh. And now what the user would do is they would move these bubbles around in space and want to get like corresponding deformations. And how we sort of incorporate this in our framework is, okay, we say we have these prescribed nodal positions, which are the small axes. And we want that the actual node positions of our mesh sort of are at the same positions. And to have this as a penalty term, a quadratic penalty term, and there's some weight in front of it. So we use in a soft penalty version. And then you have the same term as before over here, which says, okay, but also the shape that I get, this immersion that I get, it should be at least close to something I would get out of my model that I've created from data. So this is basically sort of now the prior for my problem to get like nice appropriate deformations. So basically it's a minimization problem. I have two components. You minimize for a space on my point on my subspace, on my submanifold, my SPGA submanifold, and an immersion. And these two, they should match. And the immersion I get should match the constraints being given by the user. And it's a good sense also to sort of do this in a soft fashion, because otherwise, maybe if the user does give some that are not fulfilled, it cannot fulfill actually, those hard constraints would sort of break whatever going on. So it's good to use the soft constraints. And yeah.
Okay, so just to be clear, it means that because if I understand correctly, in everything you present, there's a very heavy pre-processing step to train the networks, etc.
Yes.
So in practice, okay, if in your data set, in your training data set, you have this person running, and then what's going to happen if the artist tries to take the hand and put it very far on the left, is that it's basically not going to work. The person is going to stay like that because
So actually, I can go back to the slides. Actually, this is a slide that demonstrates exactly this, because they also have done this for a horse, not just for humans. And for this horse, we only have a model where it's running. So there's only one sequence of this thing running, and now we can ask what happens if I float my light to the side, right? And so maybe you know this one, this is some previous method, we can really see does some like strange thing with this leg. But actually with our method, which is this one, and also this one, but basically this one, we see they get some like nice, reasonable formation. Because there's still this underlying shape space that sort of has a notion of this elasticity notion in it. And this combined with this data model, even if it's not completely there, seems to be enough to also be generalized well beyond.
Okay, so because my understanding was that basically you wouldn't be able to generate things outside of the linear span of the stuff that you have already observed.
So it's also the subspace is not one-dimensional. It's actually something like 5-dimensional, but to sort of separate different leg movements and so on. And sort of things, but yeah, it's still some of the combination with the elastic. There's of course no guarantee for this, right? We cannot give you a formal guarantee this will work. But what we observed is works pretty well, also generalized beyond what we can do before.
Okay.
Let's jump back to the right. So this then is a simulation example, and we see here you have a sort of a simulated editing sequence where basically you have a movement of these points around in space, and then you follow these movements and optimize this. And again, because this is an incremental movement, you can actually do this sort of really more basically in sort of real-time fashion. I mean, it's not. So it wouldn't be the nicest user interface, let's say this, right? So it wouldn't be nice if you just start to drag your handles, there would be a bit of lag behind and so on. Well, it's actually not too bad. You can sort of work with it. I guess like a true artist would still like freak out because it's so slow. Okay, maybe, but so there's still work to do, but it's actually kind of amazing because all of these things before, if we just have done this just in sort of this frame that we've been using with this nonlinear elastic energy and so on, this would have been for each frame in an order of seconds, right? And now it's really like milliseconds, so it's really, really fast. And that's kind of cool for my sort of like this approach. And it also gives us, and also what's also been nice about this project is, so I talked about this network-based approximation, right? We started with this grid-based approximation, and now we started to switch to this network-based approximation, and it was pretty cool to see that A, it helps, and that B, if you do it naively, it doesn't help. So there's some like value like to understand the structure of the space that we're working in, to explore the structure even in this context using neural networks to get this working. And maybe let me say, for this example, actually, they were showing you right here, has been done with the grid method before. So we have not been, so just be completely honest with you.
Okay. And so just to be clear, because about this neural network, you use it specifically to compute the exponential map in the length angle space,
Yes.
right?
Yes. This also helps us because there's a lot, you don't have to deal with invariances again with the body motions and so on. And you get away with more linearity in your operations than you would in null position. So this is really, this representation is also for us has been a very important tool to make all of this happen, to make all of this work. All right. I think this, I also am time is advanced, so I could talk about more things, but maybe I come to it.
Thanks.
So if you want to, we can still talk about PDE problems. I have another 20 slides on that. I also have another 10 slides on shape spaces, so don't worry. All right. So is there further questions on all of these kind of things? Maybe. Yeah, sure.
Yeah, so that's this last model with the PGA. So you have, so you just exploit the manifold structure and not the variance of the nodes, or do you, or maybe I.
So okay, so I mean for this one, yes, this one green.
Yes. For example,
Okay.
here you do not. I mean, all the modes have the same same. I mean, for example, if you switch the modes.
Doesn't matter.
You permute, doesn't matter. So you don't have you don't.
Yeah, we
incorporate
only,
the variance in
yes,
the-
we only use the modes. We do not care about how important they are in this approximation thing. Yes, only use the modes.
Okay. But still, you could compute with knowing these variants. You could compute how plausible is one movement.
Yes, yeah.
From
Yes. So there is more to be gained from this Sparse PGA or PGA than we will do right now. Right now, it's just for us to get some kind of submanifold that is parameterized over some low-dimensional space. That's all we care about in this kind of scenario.
Yeah. So maybe just a remark. I don't know if you've started working on that, but for me, one of the core messages of your talk was about this angle length representation. It's funny because that in the protein science, it's something which people really like, to do learning or just to represent protein configurations, like Slavica is doing. You really find the same figures where basically you represent the configuration of your sequence of amino acids as the sequence of angles, and currently people want to do learning in space, so that you have all those diffusion models expressed in those basically implicit representations. So I don't know if you've ever talked to people who do that.
So I think what's sort of different is maybe that here really the structure is fixed, right? I know a priori which kind of edges and bending and lengths I can have. They are fixed, they do not change right now. As sort of also, of course, the huge downside of this like length and angle representation is really fixed to like one specific mesh. And sort of one thing that maybe will really help with this is how to, because okay, maybe another way to say this, so we have not been dealing with a shape matching problem here, right? We assume this to be solved. And you can, of course, criticize this about our approach is that maybe if you have more realistic data that's not pre-processed, then it's not solved. And maybe you want to use the same framework. And for this would be like one challenge to integrate this as a service kind of thing. But we just think of, maybe this is somewhat related, but I guess of course, the structure itself has the length angle structure is a lot bigger. It has more structure in it and also is more forgiving. Because if you make some error somewhere, it's maybe not too important. As if you have only like a small structure with a small number of angles, it's quite things maybe.
I know because you worked on that, and in Wisławica we should start a PhD on conformational manifolds. So it's like you know the structure because it's basically given by your DNA, and you really wonder like exactly what are the articulations of your protein. So that's
we haven't talked about it.
And then another question is, okay, now today, what are your main computational bottlenecks, both for processing and for rendering?
Yeah, so the main bottleneck here is actually really for this kind of thing is in the Gauss-Newton method, because you still have to compute sort of the steps and you have to compute the inverse of this Gauss-Newton approximation of your Hessian.
Yeah, so in the Gauss-Newton to do what? Because
okay, so
all the different.
Okay, so Gauss-Newton method is basically sort of a special variation of a Newton-type method for a nonlinear least squares problem. We exploit basically the special structure your Hessian of this problem has, and we can ignore like really the second order derivative part and only take the square of the first order derivatives. And then, but still there you have to solve like a linear problem, like a normal problem to get your update step. It's just still much faster than to do gradients and or something like this. We still have to solve a linear problem, which is sort of the bottleneck really here, because this is, so if this whole thing takes 30 milliseconds to create, solving the linear problem takes 20 of this. So this is the huge bottleneck here. So basically the idea is in other words, the bottleneck here is the connection between edge lengths and angles and vertex positions. So one thing you can think about is, okay, actually, maybe we can actually also make the network go to like vertex positions. So basically just the final network, and instead of letting it go to like edge lengths and angles, make it go to vertex positions. This would help us a lot. It's some idea we have yet to try, so we have never done it. But yeah, that's sort of the connection between these two spaces, sort of computational biggest bottleneck in a sense. Of course, like offline phase is expensive, right? You have to sample these things. This takes some hours. You have to train these networks. But if you commit to it, you can create this model, like this offline model, in like, let's say within a day computational time. So this is okay for what we do right now. This is something that we do not. They can also be optimized, but you can also buy a bigger computer and it's faster.
Yes, just clear, because my understanding is that in graphics, when you say a day, you mean a day on a laptop with a CPU, not a day with a GPU cluster.
So again, a day on a machine with an NVIDIA A100 and a decently sized CPU. But again, the training of the networks takes of this. So if you need the A100, it's maybe like 3-4 hours to train the networks. And then to compute these samples, that's actually what the time is, which takes like 6, 7, 8 hours, let's say, depending on how many samples you want and how complex your model is, and so on and so forth. This will maybe this just needs a good CPU, because you would just want to parallelize it and like on as many cores as you can have. So we typically do this on some like, I do it on some like AMD dual processor thing we have with like, I think 64 cores or something. I have 128, not 64, I think. So, but then again, so these things that you have, and then, but the idea is that then this online phase, really this part actually that runs on my laptop, right? So actually this was here like real time. That's this computation and online editing phase. This is really run on my laptop without parallelization.
But then it's like C++, I guess, or
yes. So I mean,
there's no way.
So the networks are in Python, but actually the proper application for doing this kind of simulation is all in C++.
Is this one how many degrees of freedom you have?
This mesh?
No, for the basis. No, for the
So it's
modes.
It's 40 modes.
40?
14, yes. You could maybe get away with less, but so the cost in terms of modes is typically not that big. Also computing modes cost you maybe like 5-6 hours. That's the part in take it to the day.
What is funny in that example is that in fact you have the guy is bending his knees, but in fact you have no marker on the knees. You have just on the
just what I'm saying is, okay, the feet have
on the top of the head.
the feet have to stay on the ground, and I push everything else that's on top, like the arms and the head. I push it just down.
Yeah.
The sequence, for example, I created manually by sort of like playing around what looks nice and what exhibits like different behaviors. Yeah, just here's me. But it's that's sort of because the model it says, of course, you should move from the knees if you won't go to get down. It's like the energetically like the cheapest thing. So yeah, works kind of.
Maybe you should stop with the questions.
I have nothing else planned.
Okay.
Yeah, I can ask you later.
We can pursue Pierre the coffee.
Okay.
Thank you.
Thank you.